So for those of you guys that were in classes where we couldn't quite finish these notes, this might be something you'd want to watch before you watch the other two videos. So I'll try and make it kind of quick, but I think it'd be best if you had this background before you did watch the other videos. All right, I think during class we looked at secant slope. It's a change in velocity over change in time. We had this expression. We might not have written this down. The only difference is that I've canceled the ones here and I'm left with h. So just pick up wherever you need to. Fast forward in the video if you already have this to the point where you're joining me with what you need. All right, the tangent slope at a equals 1 is what we wrote down. This is the notation that represents those words right there. And the tangent slope can be found by taking the limit of secant slopes. And as mentioned earlier, that h and delta x are used interchangeably. It doesn't matter which one. I just wanted to make sure that you were aware that h and delta x usually, represent the same thing. All right, so anyway, for what we were doing, remember we said we think that the slope of the tangent line to the graph we were working with at x equals or a equals 1 is -3. This is going to actually find it for us. So setting it up here, okay, and we're actually finding the slope for this function over here. I don't know what happened. And then for this difference quotient right here, I need f evaluated at 1, but we already saw that on the graph, and that's -2. And so what we need is an expression for the function evaluated at 1 plus our h, but in this case we're using delta x. And so what we did when we learned about setting up a difference quotient, we just put this input in for every x up here. Now we're going to have a lot of calculations to do, but we'll manage through it. So I think we might have gotten to this point right here. So let's go ahead and come down here. Be diligent in bringing down the notation until we're done with the problem. So keep bringing it down. That's not too much to write. The limit comes down throughout the problem too until we actually plug in 0 for delta x. So let me set up the difference quotient according to these y values. So this whole expression right here will be replaced with this output. So whatever number this is, I'm going to cube it and perform all these computations on it. So this represents a number. Okay, and then I'm going to subtract f of 1. So subtract a -2. It's all over delta x. Okay, at this point, what we can do is see if I can plug 0 in and get an answer. But if I plug 0 in, I'm just going to get indeterminate. So that tells me I'm going to need to do all the expansions. All right, so right here, if we were to cube this, expand it, multiply 3 of them out side by side, FOIL 2 of them, get that answer, multiply it by the third binomial. Okay, I'm just going to give you 4 terms, and those 4 terms that I write down here are going to be actually the result of cubing that quantity. One plus 3 times delta x plus 3 delta x squared plus delta x cubed. So these 4 terms right here just came as a result of my cubing that. Now jump back into the problem, distribute the -6. Do a little cleanup here. That's going to become +5. All right. And what should happen is thinking about the past and what we've done with limits of this type where we get indeterminate. Okay, what should happen is we should be able to clean up the numerator to the point where everything that's left should have a delta x factor. And once I factor out the delta x and divide it out of, reduce it from the bottom, I should be able to calculate this limit answer, which is going to give me what I think is the slope of the tangent line that we estimated to be about -3. All right, so let's come back in here and kind of clean this up. So I'm going to take 1 and add it to 5. That's 6. Then I'm going to go back and look for any other constants. Yes. So I have 6 minus 6. Those take care of each other. All right. Looking at what all the terms are that I have left, notice that they all have a delta x factor. And if you notice that that term and this term are like terms and you can collect them, you can collect them right now. Put them together as -3 delta x. If you don't see that, it doesn't matter. It will take care of itself in the end. And I'm going to purposely not collect them. If I did collect them, I'd have minus 3 delta x's. So I'm going to purposely not collect them. No, I hope your lines are straighter than mine. All right, looking at the remaining terms, I'm going to factor out a delta x. So out comes delta x, divide that out, leaves 3. Take 1 out here. You have 3 delta x. Plus divide out a delta x here. That would mean you have delta x squared. Divide out a delta x here. That would mean you have minus 6. And we still have delta x in the bottom. All right, think about what we do next. The whole reason of dividing out delta x is so I could cancel those. Okay, and actually, now I can plug in 0 everywhere I see delta x. Well, when I plug in 0 for delta x, this term will go to 0, and this term will go to 0. All right, next line down, we're going to have the slope of the function at 1 is equal to, all of this is going to simplify down to an answer. And that's our answer for this notation. So 3 minus 6 is negative 3. Just what we thought the slope of the tangent line would be, but yet we've actually found the slope to be that number. All right, so that concludes the objective of finding the tangent slope at a equals 1. Sometimes, though, one more quick thing, sometimes they ask you to write the equation of that line that's tangent to the graph. So let's review that. We're actually going to give a name to that line. So the tangent line equation at a equals 1. Notice I just found the slope here, but I want the full-blown line. And almost exclusively in this class, we do use point slope. Ooh. All right, so it's good to find the slope, but also one further thing you might be asked to find is the equation of the tangent line to the curve at that point. Almost exclusively, we use point slope in this course. It's not wrong to use slope intercept. It's just more common that we use point slope. So to remind you about point slope, here it is. Y minus y sub 1. And the slope times quantity x minus x sub 1. So if we're going to write the equation of that tangent line, we're going to use this formula. All right, and so we need point and slope. That's why it's called point slope. So the slope we're going to use is actually this value right here. You've come to know that as m, but with new calculus notation, it's f prime of 1. If you want to use m, that's fine. M equals negative 3. And the point is going to be 1, negative 2. So this is x, this is y, and actually this is x sub 1, y sub 1, and this is our slope. So let's just dump everything in. So it looks like y plus 2 equals the negative 3 we found times quantity x minus 1. You can get y by itself if you want to move the 2 over, that's fine. Otherwise, we just typically leave it in this format. So the ultimate objective of this was, of course, to find the slope of the tangent line, because now we know the slope of the graph. But oftentimes you're just asked to find the equation of the tangent line, which means you have to go through all the previous process and then access your point slope formula and dump in the slope you found and the point you were using. Okay, so that is an objective as well. All right, so the video notes kind of pick up where we leave off here and present you with another situation regarding the same graph.